much.
Well, yesterday I was talking about topological invariants and about the cases where the topological classification can imply the analytic one. Today I will look to a different problem. It's somehow a continuation of what Frank has speak about. He already has talked about the Poincaré theorem that allows us to linearize a vector field locally. So what I want to look today is the case if Frank talked about the case where we have a linear part and terms of higher order and give us the conditions where one can linearize this in an analytical way under the hypothesis of Poincaré theorem. We can do this. I will talk now about the case where this A is absent. That is, I will look to the generated vector fields. They have no linear part, and I will be interested in look what is called nowadays the Thom's problem of analytic classification of the generated vector fields, holomorphic germs of vector fields. This problem is to find, I will write it, but I would like to first introduce the problem, is to find the minimal set of invariants that we need to classify two vector fields. That's to say, if we have these invariants coinciding in two vector fields, then we can say that both are analytically equivalent. So we are looking to the minimal set of invariants. So let me put the following. We may assume that under transformations, a degenerated germ of vector field can be written in the following way. It is not difficult to see that you can write the vector field in xy, and I will write it like this: p x y q plus p x y d dx plus q x y d dy. That is, you can assume that you have the axis, the y-axis invariant. It's not difficult to look the things like that. And in this, for this vector field, I will denote V0. Let me take xy r is to 0. So I am considering germs of holomorphic vector fields, and let me write as V0 the principal part of this Pn Qn. That is the homogeneous part of this polynomial and the homogeneous maximum degree, minimal degree of Qn. So I will define then we know this the set of vector fields of germs of holomorphic vector fields having principal parts V0. That is the germs written as V0 plus further linear terms. So let me recall briefly what I said today, what I said yesterday about the conjugacy. I said that two vector fields are analytically conjugated. V and W are analytically conjugated if one can send in the solutions passing through a point P by a holomorphic biolomorphism, sending the solution to one point P to the solution to another point at. So this was the statement defining the analytic equivalence. This is a biolomorphism. And if we want to work with formal normal forms, this is nothing, because we don't know about the solutions, and it is difficult to work in this setting. So we can do what we cannot do while working with homomorphism. When yesterday I talked about H and homomorphism, and I wasn't able to derive, but at this moment I can take the derivative, and therefore I will write W as the derivative of H multiplied by B H inverse at X dot X. So this can be understood if I am working in the formal case as an equality coefficient by coefficient. I will be interested in sending not the solution with the parametrization, but curves to curves. So I am interested in looking to the foliations that are induced by the vector fields. Therefore, I will be able to multiply by a function, and I will use this equivalence in the following case. I will ask the derivative of H at 0 to be the identity, and k of 0 to be 1, that I will call, if I have all this, I call that V and W are strict analytically equivalent. Or if I am looking to the formal case, then I change this for formally equivalent. So these are the definitions that I will use, and this normalization was only while one works. It is only to work more comfortable. Well, I will use the following. Let us take this principal part and define the following. Let me see, maybe here. Let me define Rn plus 1 of xy to be I will forget this yq or xqn xy minus y n xy. This has to do with the age of Frank. It's more than that. We define this number, this polynomial of degree n plus 1, and we will distinguish two cases. We have two cases. The case Rn plus 1 identically 0, and this case we will call the diacritic one, and the case where Rn plus 1 is not identically 0 and is the non-diacritic case. So, in what those cases are different? If you take the blow-up procedure that Frank explained this morning, you will have that in the blow-up of the diacritic case, you will have here the singular point will be substituted by a sphere, and there will be the solutions will cut transversally, but in a finite number of points where there are tangents. So, tangents. So, in these cases, you will have in these tangencies, when you go down, this is imagination only. It's a real design of something that is complex. So you will have here the solutions, and you'll have something that is cutting. Well, maybe something. And in the non-diacritic case, you will have again the sphere in the blow up, this is hole. Sphere. And everything are surfaces, complex surfaces. And you will have a finite number of singular points. That is, in the non-diacritic case, the exceptional divisor will be a solution. And you will have some singular points that come from the roots of this polynomial when you look into it in the blow-up. So you have here, you will have some separatrices and you will have the nice solutions. There is space to do this. So you have here the solutions, and you will have also here the holonomy that I talked about yesterday. You will have for each point, I am going to put here a transversal solution, and I will take a point here and a point here and look to the loops going around the singular points on the sphere, and they will give rise to an holonomy. Holonomy group. So here I will have G. Well, I will write it later. Let me now put the following questions. We will be interested in look to both cases and to answer the following questions. We would like to know what is the formal normal form. We would like to know if we have something as we had yesterday, some kind of rigidity. We would like to know if the weakest equivalence implies the strongest one. So we want to know if we have rigidity, that's to say formal classification implies analytic classification. Yes. Or equivalence if you want. Formal equivalence implies analytic equivalence or foliations. I am talking about foliations. We would like to know about the invariants. That is the Tom's invariants that of analytic classification. We would like also to know if we can realize these invariants. So we would like to know if we have a realization theorem. Of invariants. And the last, I raised, in the case that Frank explained to us we had the Poincaré theorem, and we looked at, in that case, the equation is analytically equivalent locally to its linear part. The proof for this theorem is to look that the formal normal form, the way to get the formal normal form, is a convergent one. And in this case, it is the formal normal form coincides with the analytic one. So we want to know if it's true, the formal normal form, if it coincides with the analytic normal form. So these are the questions, and I would like to talk some about them. I will strict myself to talk about this case, even though there are answers, analogous answers to this one. So let me be working in this case. Okay. So the first question is to look for the normal formal form. So let us take theorem. This is a joint work with Ernesto Rosales and Sergei Boroni. Rosales and Boroni. And it's the following. Let B not be a generic generic. Let B not be generic, and let B be a germ of vector field that is contained in this set. Generic also. And let B be generic. Then the formal normal form for B is, I will write it like this, B, C, D. It is written like the principal part that was fixed, yes, plus this part that will be a Hamiltonian polynomial, plus something that I will write like this, bxy multiplied by a radial vector field. BC is, let me write like this, minus h y h x, and h is the sum from j bigger than m and m plus 2, and yes, I j is no bigger than n minus 1, c I j x I y on and Y is polynomial on Y. It is a polynomial on Y of degree n minus 2, and that's all. And the coefficients are a formal series on B. That is the formal normal form that one can get, and it is unique once you have done this normalization. Well, the genericity assumptions on V are, on the principal part, are that you will have n different singular points at the blow up. Oh, I forgot here to put the picture. These are the separatrices that may arise. And we assume that we have n different, n plus 1 different singular points. Then the zero generic is that we have n plus 1 singular points in the divisor, in the exceptional divisor. And we assume also that the linear part of the vector of the fields that we have close to the singular points have the following thing. They are lambda. This is, let me write the quotient of the proper values of the linear part at the singular point as lambda. Lambda 1, lambda 2, lambda n plus 1. So lambda 1, lambda n plus 1 are, each of one are lambda j is the quotient of the proper values of the eigenvalues, lambda g1 over lambda g2. And I will ask them to be in C, but not in Q. Okay. And another generic assumption is one determinant to be, we ask some determinant to be non-zero, but it is in the proof, hidden in the proof. So I will not write then that, no? Some determinant of it's not needed to say. Now, so this answers this question. For the dicritic case, there is also a formal normal form. And now, let me speak about the rigidity. The rigidity was obtained by Sergei Voronin for foliations, and in this case is all what we want. This helps us to do the following. If we have that formal equivalence implies the analytic equivalence of two vector fields, then we need only to look to the formal classification. We are not going to look anything else but the formal series of the vector fields. So, looking to that, we have the following. We define definition comes invariants for the analytic classification of generic vector field. In here are the following: T, V, so tau V. It will be the collection of constants that appear here plus the class of strict conjugacy of the monodromy group. What is this? We have here the holonomy and the monodromy group module that we can move the point as Frank explained yesterday. So we have the holonomy group generated by G is generated by delta 1 and delta n plus 1, satisfying that if you recall yesterday, we got some exponential of 2 pi lambda 1 over lambda 2 or something like that. These are these lambdas. And we ask that these ones will, well, this happens. We don't ask, this happens. That they satisfy this condition. And we will say that we are in the class of a strict conjugacy if we have another group G tilde generated by different delta 1 and delta J n plus 1 tilde, and we have a biholomorphism conjugating the delta j's. Delta j is equal to delta j tilde h for every j. They are equivalent, analytically equivalent, and we ask h prime 0 to be equal to 1. This is the strict class of conjugacy. So we define these two things here, and the theorem is that if B and B tilde are generic terms in B0, where B0 is generic as in the theorem 1. Then the coincidence of tau and b-tau tilde implies the analytic equivalence of the foliation FB and FB and FB tilde. So this is analytic equivalence. So this means that what we need to have, if we have the coincidence of these constants and the same class of strip conjugacy of the holonomic group, then we can say that both foliations are analytically equivalent. Okay. We would like, these are the tons invariants, and we would like to know if we can always realize these invariants. The answer is yes. Here it is. Here. The invariants that invariants can be always realized. And when I say always, you need to the following. You need to ask to give a group that has these requirements of the lambda j's associated to the delta 1 and delta n. If not, you will not have it. You have you need this assumption. In generic, in this theorem, we assume to have the genericity conditions that we have here, but also we need to ask that the monodromy group is non-solvable. The non-solvability of the holonomic group is necessary here to continue to work. It was necessary for this theorem. So we need to ask this condition to get that theorem. And the last, of course, the same questions were already answered for the diffuse case. The invariants in this case are, if you look here, when one has a tangency point, here you will have a kind of involution. So these involutions with proper parametrization and some constants as we got here will be the invariants for the diffuse case. But I will not go there. I would like to say some words about I would like to say some words about this question. Does the formal normal form coincides with the analytic normal form? The answer is perhaps it's not the case. It will not coincide, but if n is equal to, they do coincide. That is for generic, I erased, for the generic term, if you don't have the linear part, you will have generically a quadratic term. So in this case, they will coincide. The proof for this is more or less like the lines are follows. The formal normal form for this case, if you look, I hope I did not make a mistake. If you look to this, if you look to this, you will have for n equal 2 and n equal 3, this will not be present. For the cases n equal 2 and n equal 3, you will have no Hamiltonian part. You will have the principal part, homogeneous, quadratic or cubic, but in this case quadratic, and a radial part. So this part is absent, and the radial part will be something very cute, very nice, because it is a polynomial on y of degree n-2, but n is equal to 2, so you have that you will only have a dependence here of x. V is v of x, and is simple. I did not mention, but is you can have also the degree, not the degree. Well, you can write this v in an easy way. So there are a few parameters to work with. So the idea is the following. I am very happy that the author of this idea is present, is Frank Loren. He used the idea that I am going to talk about now for a different case, for the case where you have a nilpotent linear part. And we like it so much because to talk about the convergence of the formal normal form, you need to make classically a lot of computations of convergence. It was the Takens normal form, and there were, I think, at least 30 years that no one answered to this question, if the formal normal form and analytic one. And Frank looked to this question in a really geometrical way, and I will adapt this way to our case. So, the idea is the following. You have a singular germ, quadratic, beginning with quadratic terms, and you have the singular point, and you can, if you remember, I said that the y-axis was invariant. So you have this as an invariant, and I will take a neighborhood of it and look to the blow-up. I will look to the blow-up, and you will have here the blow-up, and you have the, I will use also what you have talked today, the Camacho-Sad index. I will say that the Camacho-Sad index is lambda infinity, and I will look to, and you have here, here lambda infinity. The other, if you calculate the Camacho-Sad local index in this direction, and you make the calculation in the other direction, you will have that one is the inverse of the other. So you have here this Camacho-Sad index, and you can make a construction of a vector field that will extend this vector field, a construction like this, having here a singular point of the type with a Camacho-Sad index 1 over lambda infinity. Okay? And you put it like this, very simple vector field or bundle. And now you do the following. You do it taking the things properly, so that you can now, you forget about the blow-up, but you don't forget about this construction. And you now glue the following things. You have here your singular point. You have here the separatrices. You don't lose information. You know that this separatrice is present. So here you have. And you now glue. You are going to be able to glue this construction. Oh, sorry. Oh, maybe. I don't know. Maybe it. And you have here your -1 to lambda over lambda infinity. You have here the singular point that you have there. You glue, and you remember that, well, that was maybe not said, but when you have the Camacho-Sad index and you go down, you will gain one number. If you have here 1 over lambda infinity, here you will have, with respect to this separatrice, you will have 1 over lambda infinity plus 1. What we are looking to have is a normal bundle to the sphere that is here. One can say that it's Brauer or Sutherland. Brauer is suddenly made it for zero index theorem, it tells you that this is the product of the sphere this is, excuse me, the product of this open set to CP1. So you have a product, and in this product you have the vector field that you have here. It is the x and the y. It is not the blow up. It is y here, x here, and what I am saying is that the vector field is defined everywhere. So it has to be polynomial vector field because it is defined along every CP1 and the spheres. So this will tell you that you have a vector field polynomial on Y. So after that, what you have to compare is what you get there and what you have in the formal normal form. And make some computations to look that you have exactly the same coefficients, and therefore the formal normal form will be the analytic one. And this ends this question for n equal to. So that is all what I wanted to say. For me, is a question that I would like to understand. Of course, the CIJs are somehow related to the separatrices, but they are not the separatrices. The separatrices are not exactly the invariants. One would like to understand these coefficients. The same goes for the case of for the dicritical case. There are also some coefficients, and one would like to understand geometrically exactly what they mean. So thank you very much.
Do you have any questions, comments? No? So let's thank again Laura.